Well, I'm Jim Kleiber. We're in Science in the Valley, Sci-TV, and we're today at the Carnegie Library in Turners Falls, and we have some whole school kiddos that are here today. And I don't know, do you want to introduce yourselves around?
I'm Fala. I'm Raven.
Nice to meet you.
I'm Pax.
I'm Pax. Are you guys excited for the show?
Yes.
Awesome. It's going to be a good one.
So the last week we had little circuits, and we had a battery and a wire and a light. And when that happens, electricity leaves the negative end of the battery and comes around to the positive end, and that makes up a circuit. And that's called current electricity. But there's another kind called static electricity. Anybody know what static means? What's it mean?
It means like something sticks up.
Well, it certainly causes that, but not quite what it means. Somebody will talk about a static situation, which might be, static means not moving. And so static electricity is electricity that is not moving. So this here, this is a Van de Graaff generator, and it generates about 500,000 volts. And the way it does it is there's a band in here that rubs against the nylon and a wheel, and all those electrons collect here. But if you look here, all right, this is plastic, and this plastic is not a conductor of electricity. And so these electrons on here, they like to get to ground because they're negative, and because they're negative, when they get anywhere near ground, they pull on those atoms, they pull on the positive part of the atom and make the ground positive. So anywhere electrons are near the ground, that's where they want to go. So, but this thing here is nice and isolated. Same with the balloon. So we can charge these up with static electricity, and they will hold that charge. So one of the first things I wanted you to do is we have what are called static electricity boats, and I'll show you what they are. What you're going to do is you're going to make a little boat like this, and then you're going to make a little sail out of tissue paper. And then we're going to put some water in here, and you're going to put your boat in the water. You'll rub this comb, and I'm going to give you some wool. All right, we ask you to use the wool, and you're going to rub it on that wool, and then you're going to touch it to this, and you're going to charge it up. And once that gets charged up, it's going to repel. And your job is going to be to try to get it from one side of the table to the other side of the but you can't touch it. So if you want to come up, we'll get some stuff out here. I'm going to put these here. There are packing peanuts here. Some of the packing peanuts are more environmentally friendly than these. They're made out of starch, and so come on over, grab a packing peanut, grab a and there's some scissors, and here you can pick a color. Just take a little piece off of here, just cut a little piece off of this, so you can pick a color that you want for your sail. And the sail should be about the size of a postage stamp. And so there's some scissors here, and like I say, you can pick a color over there, and you're going to need a... All right, so... Static electricity boat races.
They're
pretty good, except for the room isn't level.
About that big.
Ooh, I put enough water here. Wow. see if we can find a more level spot for this. A little light in this corner over here.
Here's your boat.
Okay, there's your
I think
boat.
it might be easier to.
All right, I'm going to give you some wool. So you take a piece of wool or anything you find here.
Yep.
All right, and yeah, put it on your. So you're going to build up a charge in the comb. Electrons are going to go from you to the comb, and then you're going to put it from there to the sail. You just touch the sail. Now, once the sail gets it, the sail is charged with electrons, and the comb is charged with electrons. And guess what? They don't like each other. So they can be pushed along, and you don't have to touch them. Okay. If your sail falls over, it gets wet, and you need a new sail. So part of it, you might want to try before you put your sail on, is just to try and see that your boat is stable. Okay, so, all right, so you're pretty charged up there, so just touch your sail. All right, now, all right, okay, that sail likes it, so you know what, you can drag it along. Sometimes, okay, but you want to do it without touching it. Let me show you here for a second. See, you don't have to touch it.
Wow, that's like magic, huh?
There you go.
I think you're supposed to hold it and then go like this.
There you go. Okay, you can give that a shot. If you do this, like this, you take thing like this,
Too far away.
and then you go like this. All right, that will get it pretty charged up.
Whoa!
Yeah, you can really zip those things along.
You can even turn around.
Yeah, you're right. All right.
Like this.
Very nice. If you have a competitive edge, we do boat races, but some people don't like the competition, so we don't do that.
Does the color of the sail affect how fast it goes?
You think? Oh. Oh, yeah. Oh, yeah. You don't have to do it very long. All right, give it a shot. Yeah, just very gently drop it in. How'd it go? Oh, we get our sail wet? If your wool gets wet, just take another piece.
It's not wet, stay dry.
Yeah, if it stays dry, you're okay.
You want to do yellow again?
Or maybe that.
You know what you might want to try is just put it in the water without the sail and make sure that it doesn't tip over. And then you know it's stable.
So why does the water kill the charge? If it gets wet, it stops working.
Yeah, the charge that goes into ground, there's enough salts in the water so it will dissipate. Yeah. Plus the wet tissue won't hold the charge at all. So
So if you put the
It's
comb
okay.
in the water, you'd have the same problem.
you probably would discharge the comb, I would say. I would say.
Maybe mine needs some more charge.
How are we doing here?
There was
If you-
Charge it up, you have to touch the sail.
Yeah, if you have a lot of trouble with that one, try another little peanut maybe if it's not.
Your hands dry?
There, superpower.
There you go. So are they charged the same or are they charged oppositely?
Opposite.
Opposite, exactly, because opposites attract. So that sail is oppositely charged.
A supercharger.
Oh, there! Whoa! Holy moly's! Wow!
Mine's going round, going round.
There you go. There.
Who knew you'd be yachting in science class?
Right. 3-penny yacht here.
3-penny yacht.
Yeah.
Yay.
Yeah.
Hey Dad, can we make this at home?
Uh-huh.
You sure can.
This is going to be so fun, and Theo's going to be so freaked out.
Oh, good. Well, I have.
Take his big paw and slap everything.
I have plenty of packing peanuts, plenty of,
My dad already has some.
and anything you need, except for the combs. I think you'd probably have a comb at home. Yeah, I'm probably the least likely person you would think would have a lot of combs, but there it is.
I think we need
More
to
than
work
one use for a
on
comb.
toothpicks. I'm gonna charge mine a little more.
Okay.
Why do combs work so
The combs, well, they have a lot of surface area because of all the more surface area you have, the more charge you can hold. That's why the electrostatic generator holds so much, because it's got a big surface area. You have all those little combs, so you got all those nooks and crannies to stuff electrons into, because electrons don't like each other, and they try to spread apart as much as they can to get more surface area.
Back,
What was your
back
question,
to the
Raven?
shipyard. I said, when is our hair going to stand up? And Kessie's fur.
I don't know about Cassie's fur.
Yeah.
That might not stand
No.
up.
Yeah, it's not. So it's not.
Otherwise it would have melted.
So there's a famous picture, I think it's of Nikolai Tesla sitting in a room reading a book with lightning bolts going off all around him.
Yeah.
Wow, you can actually
Yeah.
smell something on this.
Yes, Nikolai Tesla, he did a lot of things, many of the things like AC generators. Nikolai Tesla,
About 100 years ahead of his time.
yeah, Nikolai Tesla worked with Westinghouse and tried to convince the country to go to AC current,
The other boat.
and that was quite a battle in doing that. And some places are actually wired both AC and DC.
So it doesn't fall over. Mine is moving over.
Oh no, yeah.
Ooh, we're gonna go.
There goes my ship.
Ooh, close, close one. So I want to tell you all something about how important electrostatics are. If you could take the inside of an atom, anyone know what that's called? Atoms have a very tiny, very heavy center. Anybody know what that's called? Called the nucleus. And around that nucleus, the electrons that we're moving around, that's where they go. Well, let's suppose you had a magic wand and you could take the nucleus of an atom and make it the size of a pea. That's immensely larger than what it is. Well, if the nucleus became the size of a pea, then the atom would be the size of a football stadium. And guess what's in most of the atom? Nothing. So picture this. You have,
We're mostly made up out of nothing.
yeah, so if the nucleus is the size of a pea, the electrons would be the size of a speck, like a dot on the end of a period, and they're revolving around this thing. But it's the size of a football stadium, and it's all empty space. So when you think of it, atoms are about 99.9999999% empty space. So you might ask the obvious question, say, well, wait a minute. If atoms are empty space, why can I sit in a chair? Why don't I just fall through? Wouldn't it make sense? If atoms are all empty space, then what's going on? Well, electrostatics, and you can be darn thankful for it, because the outer part of every atom is an electron. And so the outer part of all the atoms in your bum are electrons. The outer part of every atom in your chair, that's electrons. And because electrons repel, they keep you from going through the chair. So what keeps you from falling into the earth, because matter is mostly empty space, is electrostatic charges. Electrostatics, very cool. So, something else over here, if you're ready for it, or we can spend some more time with the, this over here is the Van de Graaff generator. And over here, these are called, they're called fun fly sticks. And they generate a charge. And I'm going to put this right near you. I'm going to put it near your face, but you're not going to feel the shock or anything. So, but just see if you feel anything. Feel anything? Yeah? I can hear the snap.
You can hear it.
Sorry. There. So, if we take a little shape, something like this. So what we're going to do with this one is the fun fly stick is going to charge up negative. Now what I'm going to do is I'm going to drop this tinsel on the fun fly stick. And then it's going to be charged the same, and they should do what? Attract or repel? Exactly, okay. Now the trick of this, you got to watch me. I'm going to drop this, I'm going to touch this, and I'm going to pull it away. Okay, so I'm going to charge it up, drop it, and I'm going to pull it away.
Wow.
There you have it.
Oh my God, can I do that?
Yes, you can. Okay, so I've got a bunch of them up here. Some work better than others, but you can try any one of these should work quite well. I'm going to give you a cool shape.
Where do you get these?
Fun fly sticks. If you Google them, you can get them. Steve Spangler. Now these are very, very fragile. So when you get them, just try to keep that in mind. Be careful when you touch them. But they will give you kind of an interesting shape. So, if you let me borrow yours just for a second, I'll show you how this works. So, if you touch this, remember electrons repel, and there you go. Okay, all right, so what you're going to do, all right, turn it on. I'm going to drop it, and then you're going to just drop that down. Drop it down. Okay. Whoa, it likes you. Okay, go under it. There you go. But it definitely likes you. Okay, there you go. Pick your.
I think you can turn it off once you,
Yeah, you don't have to keep it running.
once you charge it, you can turn it off.
Okay, there you go.
Here we go, ready?
Oops.
I think it's the materials in our clothes that make it go like that.
It keeps coming for you.
Yeah, one of the problems we have with these are vents in the ceiling, because they're intake vents, and once they hit the ceiling, but they're charged up with electrons, and you're nice ground, so they like you. Yeah, once you got them up, you don't have to keep it running. It will, it'll keep the charge. Now, a little hint: if you keep them horizontal, you can control them better. If you put them vertical, if you got your fly stick vertical, it's going to keep on going up.
Do not fly on my nose again.
Now, the thing you might want to try is to play catch.
Oh.
Okay, so some of the adults want to join in. See if you can play catch.
Join in with the fun.
There you go.
Are you ready, Ray?
Okay,
Here we go.
this one sounds like heck, but
Oh no, it's going away! What the hell is that? Oh, it's that.
yeah, this one needs a little lubrication, but it works well.
So it's mine's and tricks. Let's try it.
All right, coming over. Can you get it? Keep it horizontal. Horizontal like this. And let it go. Okay, all right, so now push it over to me. Yep, keep it horizontal. There you go.
I can only make mine go up.
Yeah, well, let it come down. Just let it drop down. There you go. It'll come down. Gravity will work on it. Whoop. Okay, here we go. Oh, rats. Yeah. They become some interesting shapes. No, I'm trying to get it over to you. Yeah, we may need to. Okay, let's see what we got. Okay, drop it down quick. Okay, let's see it. Okay, so if you get it going like this, let it drop and then go down. And boy, did it like you.
What's that?
Yeah, but it's a friendly one. Okay, let it hit and then drop it like that, quick. Drop it. There you go. Now you got it. Now you got it. Oh, excuse me.
Sorry?
Just gonna. That's okay. I'm just gonna give you another one.
This one doesn't work.
Try another one. Some work better than others.
Yeah, see this one, maybe it affects it if it's disconnected right there, right? Maybe it loses.
Oh, you've got a. They break.
Oh, and that will
Yeah.
break the.
No, they'll still work. You can tie them,
Oh, okay, and then it'll.
and then it works again. But if they get all bunched up, then they don't work as well, doesn't it?
I know. Are you a fixinator or fixie?
If you Oops, oh, I'm sorry. Okay, you know what? I'm going to give you another one because that one's getting kind of
Crinkled.
yeah. And when it gets, I'll take that one. And okay,
That was mine.
there. That's what they're supposed to look like.
Now we've got it.
This is actually like the floor.
That's
Raven, the one
yeah,
that I had.
that's
Had opened up like.
that's okay. That's right. That's what they're supposed to look like. And boy, does it like you.
It's my nose.
Yeah, it did.
I was like,
It did.
got it. Wow, this is so beautiful, Dad.
Oh, get it.
Oh, you sucked it up.
One of the things that I love about working with homeschool students is they come with their parents, and you see the parents and the child working right together. Here you've got 3 beautiful examples of parents working together with their children, learning science. A great way to learn science. So get your parents involved with any projects you might have. You'd be surprised how much fun they might have.
Here, Jeff, I got a question for you. As an educator, you've seen kids learning without their parents and then with their parents. Do you have any words about like the difference you see? Maybe about the, when their parents are there versus when they're just in the classroom. Is there much of one, or?
I don't think so. I just think that it bonds. You get the bond between the child and the parent when they're working together in the science that you don't get when somebody comes home and says, "Oh, I've got my science homework to work on." As opposed to learning science by a hands-on activity, which is what we kind of stress here. When you do it, you don't forget it.
They got a problem up there.
Oh no. Well, you'll need to get another one. You'll need to get another one.
I think I'll need to get another one.
You gotta be careful not to keep moving.
Yeah, I'll try.
Ready?
Can I have another one in the meantime, too?
Let's see what we got here.
That'd be a better choice for me.
Let's see. We got another one.
There we go. So you just have to press it a few times because it charges and then.
Okay. All right. Try this one. There you go. But they're just tinsel, so they break relatively easy.
I saved it.
Okay, pass.
Save your phone. Got a new one.
Oh, you got it pretty crinkled up there. When you kind of grab it with your fist, you put them all together, and there's less area for electrons to gather on. But you do get some interesting shapes as they break. Sometimes they will form figure eights and all kinds of neat things. So whenever you're ready, we will get on to the next phase, which is the Van de Graaff generator. Uh-oh.
You found it? Yes.
Shoes untied there, Raven.
I don't care.
You will when you step in the shoes.
Yeah.
Your foot doesn't go forward.
So I'm going to ask all of you to sit either at the table or over here. This thing will throw a spark about 24 inches, which it wouldn't kill you, but you definitely know that it happened.
I'm going. Oh, I want to see this thing. I can't wait to see my hair sticks out.
So this is the Van de Graaff generator. It has a large belt, and it goes through a nylon wheel, and that charges up. And I have this ball, and I try to keep this between me and it, because as long as it's in between you, this is connected to ground, and the electrons want to get to ground. They'd love to get to ground through me, but I'd rather they didn't do that. So, and I put the switch over here. So, and here we got going here. You see down here, this wheel right here, it's getting coated with electrons, but the electrons are coming off the points because the smaller the point, the less charge it would hold. So any electrons it gets, and so this thing will keep turning around, and sometimes gets even a lot faster than that. This thing here, these here, remember, keep this between. This is called Benjamin Franklin's bells, and it's very feisty today. And if this works right, you may be able to hear the bells ringing. We'll give it a shot, and we'll see. Not working quite at the moment, but they will. Okay, keep this right over here. This is called the lightning plate. And what I can do is I can get a charge to follow the path that's here. And as long as I hold it here, at least we hope. And I'm not getting shocked because I'm not in the path. You can see it's doing its thing. If I put the balloon next to it, the balloon will like it at first, and then it gets repelled. Kind of like a little punching bag here. And you can actually light up a bulb. I don't know if you'll be able to see it, but it's a little bit. Not enough going through to me. This little whip is similar to the balloon, where it will be attracted to it, but then as soon as it's attracted, it comes back. So it'll kind of whip back and forth. It loses its charge, comes back, and keeps going back and forth. And that was interesting. That was from the balloon. The balloon was charged up, and as I touched it. All right, so I have a ball. Right now the ball is discharged. I'm going to touch it over here, and now it does not. I can force it to touch it, but once again, if I discharge it, I got electrons there, and it does not like that at all. There's a common thought about lightning rods. And most people think that the purpose of a lightning rod is to attract lightning, and then the lightning will be conducted to the ground. It's actually just the opposite. The smaller the surface area, the less an object can hold for a charge. And so what happens is all of this charge that's in here goes up to this point here. And at that point, that charge comes off. So what we want to do is we want to see, can this prevent lightning? So I'm going to look here. All right, I've got lightning there, but when it come up here, nothing. Not a thing. All those charges are being dissipated through there. So that's the purpose of a lightning rod. Now I can, oops, it's very feisty today. I can show you the wind which is created by the electrons coming off the machine, and I'm going to do that with a very, very precise piece of scientific equipment known as toilet paper. So some of the things that that you can get a lot of mileage out in science don't have to be expensive science toys. Now, so what we're going to do is see if there's a wind coming off this thing. And if we look at it, there you can see it. Those are electrons. That's the electron wind, which is being produced by, see, if I just leave it here, it's not going to do it. But once I have that up there, as you notice, you have to kind of follow your own advice. Remember, keep this between you and it. All right. So now we want to talk about what happens if a person hangs on to this. So we're going to use, again, a bit of, yeah, more science equipment, right. Yeah, balloons and all kinds of stuff. So what I'm going to do is I'm going to tape this on here like this, and this scientific instrument, which you see on top of the Van de Graaff generator, aka Scott's toilet paper, all right, that is going to get coated with electrons. And remember, electrons don't like each other. So let's see what's going to happen. Electrostatics are a little fickle sometimes. You don't always get what you want, but sometimes get what you need. Well, with a little thinner toilet paper, those would be straight up. But you see what they're trying to do, but they can't quite do it because the paper is thin, too thick. So here comes the big question. Who would like to get their hair raised? All right, we have a brave person. All right, so you're going to come over here. Now I can't guarantee you 1,000% that you're not going to get a shock. I can guarantee you that you won't die from it. No, we can do that. All right, so that is good. All right, okay. So we don't want you to get a shock, so what we need to do is we need to isolate you from ground. So you're going to stand on this, all right? And you're going to put your hand right over here, all right? Okay. You're a very brave soul. Now, the thing you don't want to do is don't take your hand off. If you take your hand off, you're going to get a shock. Now, if you feel uncomfortable, you just let me know and I'll turn it off. Okay? All right, but don't take your hand off, and you'll be good. We have one more thing here, one more little thing here. We need to spray you a little. This is just water. There you go. All right, you all set? Okay. Now, if you shake your head a little bit, and you are, all right, now I'm going to put this in front of you so you can see it, but don't touch me or we'll both get it, okay? Yeah. Give your head another shake. How you doing? Yeah. Wow. You are just a spectacular. How you doing? Amazing. There. Now you're charged up about 500,000 volts. Do you feel anything? Any shocks or anything? You are
That's amazing, huh?
I can see it from the clear ball.
yeah. Oh, very good. Now, I'm going to shut it off. You're going to take your hand off and watch what happens. You all watch what happens to Raven's hair when she touches the ground. All right? So I'm going to turn it off. All right. Yeah. Now you can take your hand off. Your hair's still up. As soon as you hit the ground, you're grounded, and that's it. There you are, 500,000 volts.
Yay!
All right. Okay. Any other brave souls? Oh, come up.
I can only barely see myself.
Okay. All right. Just remember, as long as you keep your hand on it, and we'll let you go. Oh, one little. This helps a little bit. Now, if you shake your head a little bit, if you have anything in your hair, something that, but you have very thick hair, but however, you are definitely getting a rise.
Yep.
Give it another couple of shakes there. Oh yes. How are you doing?
Oh, wow.
That is it. You are absolutely amazing. Yeah. And you feeling anything? Any shocks?
No.
Nope.
My shirt's still on.
Yeah. Now watch your hair when you can't, but see it? As soon as she got the ground, just charged, and she's gone. Okay. Anybody else? So we have one last thing that I always do, and this is the pies. And what we're going to do is we're going to put these pies on here, pie plates, and you're going to notice that they're going to get charged, but when one plate gets negatively charged and the bottom plate gets negatively charged, then they might not like each other. So we'll see what happens. There you have it, how to make a mess in the kitchen. So if I have a little help picking them up, I'll do it once more.
Sure.
All right, okay, just be gentle on them because they're just tin foil. We want to make sure they don't get stuck together. Oh, good job.
Anyone?
Okay. All right. Thank you.
And last.
Yeah. Thank you. Thank you. Thank you.
That was so funny. Boing, boing. I can't read the message.
You're kind of at the mercy of the weather when you do electrostatics, because if it's really rainy and drizzly, you can't really make too much of a charge. And sometimes I do this, doesn't work at all. But today, because it's a nice dry day, we're doing very well.
Here, I'll help pick up again.
Okay.
Ah.
Great use for electrostatics.
Yeah.
Make a house look possessed.
Yeah.
You can put boats around all kinds of stuff. We know discernible things. So, I have a question for everybody. Remember when we did the maglev trains on the tracks that were levitating? We had to move them down the track without touching them? Could we have done that with electrostatics?
What do you think? Well, here's the question. In order to move the car, you need a force. All right. Now, when you rub your comb on the wool, was there a force on your little boat? Yeah. When something moves, that means there's a force on it. That's Newton's first law. An object at rest wants to stay at rest. An object in motion wants to stay in motion. So something is rest. The only way it's going to move is if I have to exert a force on it. So we know we can exert a force. The question is it enough? Is it enough to make that car move? Speaking of motion, did you know right now you're going about 18,000 miles an hour? Earth's got to get around the sun, so it's pi times the diameter. Sun's 93 million miles, so we got to double that for the diameter. Yeah. All right, and it's roughly 3 times that. So if my math is correct, that's over 600 million miles that the Earth has got to go in 1 year. And I believe to do that, you got to be going about 18,000 miles per second. So you're really moving. Maybe miles per hour. Might have missed that one. So that's it today for Science in the Valley. I hope that you join in, and we will be seeing you soon. Bye now.